Right. So I finished teaching the theory part, reviewing the theoretical parts of the course. We went through everything in by way of reviewing, doing a past paper, and for each particular topic went back and reviewed the theory for that. So that now it is in your hands to do the revision. Okay, to do the questions and let me know if you're not getting the answer, if you're not understanding what the question is asking and so on, to let me know and we'll discuss it in class, or I could respond in email and so on. Right. So this is from now until the end of the semester, whenever the exam is your time. Right. So I had suggested that you start looking at the 20 is it the 2014 paper, I think it is, that I suggested, right? So to start at least looking at that, and you tell me, well, what is making sense and what not. Let me see if I can pull up the 2014 paper here, wherever that happens to be. Right. So did anybody start looking at the 2014 papers yet?
Yeah.
Right. And right now Kemaj asked me a question based on, I think, the notch filter question there, which is let me see if I can share that. Question one, right? Okay, good. Right now, everything that we did, and let me share the good. Right. Everything that we did in notch filters are what we covered in the active filter lecture 3, which we reviewed, I think, last week. And what I need you to know is basically that we create, after you have the what do you call it, the first order and first order low pass and high pass filters, that one, we can create a band pass filter by cascading two, a low pass and a high pass filter, right? For instance, the Sallen-Key type filters, which were the ones that were discussed, and we created a first order band pass filter by cascading the first and a first order high pass and low pass. So if you know how to do that, then you can derive the transfer function, which is this one here, right? Because they are cascaded, the two transfer functions will multiply, so that you could derive the transfer function of the bandpass filter here, right? If you know that, this is enough. The general form of the bandpass transfer function is given by something looking like this. Now, we didn't talk about the Q factor or the gain in it at all. All I wanted you to recognize is that if you remember to cascade the low pass and the high pass filters together, once you get the transfer function, then this now is the center frequency or the resonant frequency of the bandpass filter, the square of it, so that the resonant frequency is the square root of whatever the low pass filter's cutoff frequency was and the high pass filter cutoff frequency was. All right. So that was one. And then the notch filter is the same sort of approach, except that this case now, you have the filters in parallel. So you have a parallel low pass and high pass filter, same first order, and then you add up the responses. So if you're doing that, again, you need to, if you remember the first order low pass and high pass responses, if they're in parallel, then the transfer functions add. And once you do that and simplify it, you're going to get a transfer function looking like this. Again, the standard form, all you need to remember is that when you cascade the two, sorry, when you run them in parallel and you get the transfer function, that the frequency, the notch filter frequency is given by the square root of omega L and omega H. And that's all. Again, you don't really need to remember this. You need to remember this bit, that the cutoff frequency for the notch filter. So the notch filter response looks something like this. This frequency here, omega R, is equal to the square root of the low pass and the high pass response, the cutoff frequencies that you were given. Right? So if I were to give you a transfer function looking like this, then you could work out what the square root of this would be, what the notch filter frequency is. And if you look at it, you will see that that notch filter is 100. Right? The square root of 10,000 is 100, and there you have it if you plot it. Okay, and that was as far as we got. Right. So let me see if I could just pull up what that particular past paper question was. Where is that? Right. Right. So here, that's why I told you need to do question 1A. Question 1B, you could see what the answer looks like. It's just a simple bit of circuit theory, but it's not part of what we did. 1C, let me know if it's suddenly raining very heavy here if you are having difficulty. Right. So this was expecting you to remember that formula. I'm not going to give you that sort of arrangement. What I would ask you, or what I could ask you, is to show how you can, using a low pass and high pass filter, how you could create a notch filter, and what is the transfer function for that notch filter. That's the kind of question I can ask you. Yeah?
So we basically listen that formula there.
Pardon?
So we basically listen that formula, given that formula for the solution.
If I ask you to, what I could, no, well, as I said, what I could ask you as a question is to show how you can make a bandpass filter. If I give you a low pass filter with cutoff frequency omega L and high pass and a high pass filter with cutoff frequency omega H, to show me, to explain how we can use those two filters to create a bandpass filter. That's one. Part two, what is the transfer function of the bandpass filter, which will be kind of explaining, included in the explanation of what is the cutoff frequency of the bandpass filter, right? And that will mean that you have to at least go back to the notes and derive it like how we did, to show that the bandpass filter is transfer function 1 multiplied by transfer function 2, and you simplify it, and so on. So, and that the notch is 1 in parallel with the other one. So you add the transfer functions, simplify it, and then tell me what the answer is. Right? You wouldn't be asked I wouldn't give you something like this. Not because we didn't do it. That was not our approach. So I would not ask you a question like this. Yeah? Fair enough?
Yeah.
All right. Okay, and the other questions, these are very easy. These are very straightforward. Of this is a similar version question we did already. This was one straight out of the notes, right? Remember, there are two sets of notes. I told you there was we have the slides that we did, the PowerPoint presentations, and there are some PDFs that I gave you with extra information that has stuff in it. Okay, so you have reading. This one is in fact, when they did this question, this came straight out of the of that, and they just changed the resistor value. So don't let that bug you at all, right? In any case, you always give me. I'm not going to ask you to memorize these sort of arrangements. I would give you it and maybe ask you to explain, because we did cover something similar to this. All right. So I keep emphasizing that. I will not ask you to draw the kind of things I can ask you to draw could be this kind of arrangement, because this is easy. But if I want an explanation, I will give you the circuit to explain, right? But like if I were to ask you to draw a Zenodiode regulated circuit with a pass transistor, you should be able to do that, all right? Or to draw like on this now, to draw like we've done before, to show how you could put feedback, fallback protection on this, or just use plain ordinary overcurrent protection on it. I could ask you that kind of thing, all right? The Weinberg oscillator, you should be able to draw that. It's a simple circuit with a series R and C and a parallel R and C in it. That's a very simple circuit. You should be able to do that. And the equivalent, the equivalent circuit diagrams for the various amplifiers that we spoke about, the voltage, the current, the transimpedance, and the transconductance amplifiers, to show, to draw the equivalent circuit for it, or to draw the feedback configurations. So if I ask you to draw a current series feedback, the equivalent circuit for a current series feedback amplifier, you should be able to do that. Okay, not the schematic, the block diagram. Yeah? Fair enough? Right, so as I said, at this point in time, this is your part of the semester now. I've finished teaching the theory and going over it. If in doing this now you have specific concerns, or you didn't understand how a particular part of an answer was derived in the solutions that we have, and so on, let me know and I'll clarify it for you, or I'll explain it in class at the next scheduled opportunity. All right, but it's up to you. And some of you, I don't know how many, you said, Kamad, you said that you had started the review. So I don't know how many else I'm seeing. If you don't count me twice, there are just 4 people in the class here. So I don't know how many of you all have started to do the problems. I'm hoping that you keeping abreast and at least you reviewing the questions. Yeah. So you're all right with that?
Yeah.
What about the others? I'm not hearing. How are you all? Have you all, Joshua, Philip, Jamal, have you all started to what do you call it? Look at the past paper and do some questions now?
Yeah, actually before this, but the topic on, well, with this one specifically, kind of brain kind of scrambled, but
Which topic?
one camera was asking about
The notch filter?
right filters, right? When I had to derive the second order transfer function,
Right.
that was giving us a little bit of problems.
Okay, let me see.
So that would be like 2021 question 5.
Okay.
But that's like using nodal analysis.
Oh, okay, okay. So maybe we have the VA minus VB, that kind of thing?
Yeah.
Okay. Just let me see. So that would have been the 20th or the December paper.
Yeah, yeah.
Okay, hold on, let me see.
Like I did see the answers and how they derive it, but I tried to do it for myself and I wasn't getting through.
Well, the simplest thing for me to do in a case like that would be for you to send me where you did and let me see. right? If you have it, a scan if it is neat enough, it just has to be readable, so I can understand what you're doing. And I could see where the issue is. Let me see if I could find the solution here. Right, December. Enough, I'm not seeing the solutions online like just now. Half a second, let me see. No, but we had it just a minute. We had it in the I put it in the for us, right? All right, there we go. Okay, here. Right. Okay. Let me see. Right. So that's there. Let me get back the. That would be this field. This vector here. Right. So that the. Let me share up the actual. Good. Right. So this would have been where that is this particular approach that you were having the issue with.
Yeah, so what I didn't do was replace C1 and C2 with I think it's
SC1 and SC2. Well, one over SC1 and one over SC2.
Yeah, so I tried to solve it, but without replacing those two and having it as Z1 and Z2.
Mm-hmm. Oh, and then substitute at the end.
Yeah.
Well, and then what happened? You're not getting the answer I'm getting?
Actually not, I reach into like I don't have like my notes on me right now, but I reach into like VI minus VA and V0 minus VA. And yeah, that's like and equals to like something on the other side, but I wasn't able to eliminate the VAs and the, well, basically VA.
Right, okay. VB is V out, as we said here. And then if you know VB is V out, right? So then VA minus V out over R2 will be equal to V out over Z2, right? So that VA is V out R2 over Z2 plus V out, right? So you substitute that back. Well, you have V out here, you have VA here in terms of V out again, and then you make that substitution, and you should once you do that, and then you substitute that this is 1 over SC1, and this is 1 over SC2, then you should be able to get the answer on this side. All right.
I guess I could try that when you record and release, I guess.
Mm-hmm. Let me see. Hold on. Let me see in terms of the solution that I had. Right. Yeah, well, I did the same thing. So I substituted from here, but I had the what do you call it? I made the substitutions for Z1 and Z2 straight off. Okay. Try that way and let me see what answer you get. And if you get stuck, just send it to me and I'll see exactly what the issue is. It may be something someone else in the class or the other people in the class might be finding an issue with as well. All right?
Yeah, will do.
Okay.
I find this was like a little bit more of a technical kind of question, more difficult than the rest. Because
Okay. What will happen again? You will find in the papers sometimes easier marks to get than others, I suppose, right? So some might like the question. Surprisingly, as I showed you, all the question with the power supply, where I asked you to put in all the voltages and currents, right? That, as it turned out, when we did it in class, you saw that it was actually surprisingly easy because the information, you didn't have to calculate any resistances or anything. All you had to do is start it off with the input voltage from the rectifier, the output voltage, and the Zener diode voltage, and then everything else was just a question of using those voltages and then using the HFE for the transistors to work out the currents, right? So that kind of thing, once you understand how it's working, would have been fairly easy, right? This one, as you say, this one, well, okay, yeah, it's a little bit more involved. The other part from that same example, the bistable, was very easy. So you're going to get a mixture of those kind of things, all right? Well, what I told, as you hear me tell Kemarj, is that I'm not going to, there are some circuits I'm not going to ask you to draw. I will give you them, but there are some that you're supposed to know. And I think most of the power supply circuits, you should be able to sketch them out without any difficulty. The amplifier circuits, just the equivalent circuit, the equivalent diagram. So no circuits with transistors and the like going to appear there. I will, and I'm not going to give you any of those to analyze for like voltage feedback and series feedback and so on, because we didn't do that. The filters and so on, you should be able to draw an op-amp, a first order, and a first and second order low pass and high pass filter. If you know the low pass, in both cases, the high pass is just to interchange the capacitors and the resistors, right? And the band pass and notch, you know how to derive that because one is a cascade and one is a parallel combination of two. We only did first order, so it's a combination of the first order high pass and low pass, depending on whether it's a notch or a band pass. Yeah. The oscillators, you should know the Weinberg configuration. The rest, you know, I will give you those circuits if I expect you to analyze anything on those. And what are the circuits that we analyze? We did the power supplies, the waveform generator circuits, and the precision rectifier circuits. I'll give you those to analyze, right? So I'll give you those and ask you, well, what is if you look at it, you should be able to recognize what it is and explain how it operates. Okay, so like the triangle waveform generator or ramp generator or the flip-flop, right? Those kind of circuits, if you're given that, the precision rectifiers, the half wave and the full wave, if I give you that, you should be able to know if it's a half wave or a full wave and if it's inverting or not. Yeah. But not to draw those, and I'm not giving you the diagrams to draw from scratch. Okay. And I'll work up some, working up a couple of just general purpose sort of revision questions that I'll send out in a day or so. And but I'm acting head of the department, so a little extra tied up the last couple of days. And but I will send out some other questions, not past paper questions, but other types of questions that will help you with the revision. And the answers are basically in the notes and the lectures that we did. Okay.
So you had a department again?
Yeah, for the last 2 weeks and maybe for another 2 weeks.
Oh, it should be for good. Huh? I was not gonna say that we celebrate.
No, just a temporary thing.
It have in 2014, right? The question 4. I don't understand the part C, part 4, part 3, and part 4.
Okay,
The solution.
Let me see if I could get that here. 2014. Okay. 2014. Which question is this? Part 3? Question 3?
Question 4. Part C.
Okay, let me see if I can share this one. This 2014. Let me see if I can pull that up here. Where's that question? Okay. That's not, for some reason it's not sharing here. Hold on a second. Some things. Right, you're seeing it here now?
Yeah.
Right, so you said
Part C. And the heat dissipated in transistor 1 after 3 minutes. I don't really understand that part. Like,
okay. All right.
The solution, they took then multiply the IE across transistor 1 times VCE, which is 40 milliamps times the 30 minus 1.25. I know where they get that 1.25 from.
Okay, hold on. Okay, so let's see what the solution says for that. Stop sharing that and share the solutions. Let me see what was put on there. If I can find it. Yeah, hold on. This is 2012. Right, good. Yeah, password for solutions, right? Nice, good. Bring that up here. That is strange. Hold on. See the people here. Just give me a second. For some strange reason, I'm not seeing it on the screen when I'm trying to share. Just right. So this is the question. Right. Okay. I think there's a solution here. Is it?
That is the solution.
Right. Good. Nice.
Yeah.
Right. Good. Okay. So let's go to question 4 here. Right. So you do that. Okay. So when the regulator is delivering its maximum, calculate the maximum voltage across TR 1. So TR1, so the maximum voltage across TR1 is VCE TR1, right, which is VI max, right? So you're looking at, wait a minute, hold on. When the regulator is delivering its maximum load current, so it's maximum load current. If the regulator is delivering the maximum load current, let me see if I can get a all right. Good. If the when this is delivering maximum load current, if this is at, this is not right, max. Yeah, this is not working good with my stylus here. Hold on. Let me get something else. See, this will work better. Good. Let's use this. Good. Right. If I am delivering maximum current here, right, this is making it a little right. Maximum current here. It means that this now is at the minimum, right? So it is actually the V input. This is not working at all, but anyway, so V input, I'll just talk it through here. Here will be V input minimum, because this drops to the minimum when you pull in the maximum current, right? Yeah?
Yeah.
Right, so disagree with that answer for the first thing. It's not V input max. So V input minimum minus whatever this voltage here. Now this voltage will be V out. If this is, well, it's a 20 volt supply, right? So if that's 20 volts here, it means here's 20.7. It means here's 1.4 plus 20, right? Well, actually, I should say that is 20.7 here. So 20.7, I forgot the base voltage, it's 20.7 here, V input minimum, and then the current through it would have been calculated, I think, from the previous part of it. So it's this, so it's not 9.3 here, it will be a little bit less than 9.3 because it's not 30. The current, the base current is 40 milliamps, or the current through the emitter. What do I ask you? The maximum voltage, the base current, yeah, it would be the load current over HFE. Right, so if this is carrying 2 amps, then the current passing through here will be that divided by the HFE of that transistor TR1, so that's correct. All right, so you have 8, where are we? Right, so you have 40 milliamps and you have 9.3, well, not 9.3, it's going to be less than that, but we'll just use this for the time being. 9.3 by 40 milliamps will be the power dissipated in the transistor per second. You remember VI tells you how much power is dissipated per second. So therefore, after 3 minutes, you have to multiply that by 3 minutes, which is 180 seconds, and you get that in joules. Right? The instantaneous power is the VI, and that is what is dissipated per second in the transistor. So over a period of time, the amount of energy that is dissipated or as heat will be energy by time, which is the 9 by the 40, and they multiply by 180 seconds. Yeah, but this 30 is wrong here. I disagree with that.
How they got that 1.25?
Where are we? This is what was that is what is supposed to be here. That 1.25, this is 2.45 volts peak to peak. So that if it's supplying is a 30 volt peak, and if they replace 2.5 volts peak to peak, it means that the minimum value going to be 1.25 less than the 30 volts. Right, so that was what was supposed to be here. Instead of 30, it was supposed to be 30 minus 1.25, right? Minus the 20.7. So that was the correct value. Multiply by 40, multiplied by the 180. So this is the correct one. That's what I was saying. This one here is not. Yeah. Okay. Once you say what is happening at maximum load, when the current is delivering its maximum load, then the maximum voltage across TR1 is not 30, it is 30 minus the 1.25, because you have a 2.5 volt peak to peak ripple. So that means that the minimum is 30 minus 1.25. Yeah.
So basically divide by 2.5 divided by 2.
Yeah. If I have, so this is that is the 30 volts here. So it's supplying 30. I'm doing something, but it's plus or minus, sorry, with a 2.5 peak to peak. So that means that here to here, that is 2.5. So therefore this or this is going to be half of that, which is 1.25. So the minimum it will be is 30 minus 1.25. Right? Which is that bit here. The 20.7, well, we said that we agree with that one. The 40 milliamps is what is passing through the transistor, and the 180 is how many seconds it is passing through that.
So the first part, where it's supposed to be?
The maximum voltage across TR1. Once you're delivering maximum load current, then the maximum voltage across TR1, once you're delivering maximum load current, this is the minimum value here. So this should have been 30 minus 1.25. Right? So instead of 30, it should have had 30 minus 1.25, because they're talking about TR1 at maximum load current. So at maximum load current, the maximum voltage across TR1 is this minus the 1.25. If they were asking the question that what is the max, as a separate part, what is the maximum voltage that occurs across TR1? The maximum voltage that occurs across TR1 is when the voltage, when the thing is at no current. So when you have no current, then the voltage here is 30 plus 1.25. And the voltage here will be at no current will be 20.7. So the maximum voltage this has to experience is 30 plus 1.25 minus 20.7. But at that point in time, we're not passing any current, because the thing is offset, it won't be dissipating any power. Yeah?
And the last part, how they got the 1.4?
Well, this one?
Yeah.
1.20
plus 1.4.
20, the voltage at the output of the operational amplifier is V out plus 2 VCE. Right. Well, look at this. So you have V out, you have VBE. What is that? 1.4, right? Yeah. So you have V out here. Here is what do you call it? 1.7. Here's 1.7, right? So this now, remember that the op amp itself, the op amp is regulating this voltage in such a way that here you want, if you want here 20, here has to be 20 plus 1.4. Right, that's how the op amp is working, because if this is 20, then you need 0.7, you need 0.7. So here has to be 20 plus 1.4. And that's what the op amp is trying to maintain. If this goes up for some reason, if this goes up, this point voltage will attempt to go up. The diode is retaining here at whatever D is. This is supposed to be equal because of the virtual earth behavior of the op amp. So if this tries to go up, because the op amp needs to create, maintain a zero potential difference between these two terminals. If this goes up, it's going to drop the output voltage here to bring it back down. Right? So that this zero, the op amp corrects this difference here. So anytime you get a change in the voltage here, the op amp, because it must maintain a zero potential difference, the virtual must have the same voltage here and here. Right? Then if the output voltage varies, the output of the op amp adjusts itself to bring it back down so that the voltage here at the two 5K resistors and the voltage at the Zener is the same. And that voltage is 20 plus or minus plus 1.4, because here has to be 1.4 volts higher than here. Yeah? I didn't realize the pointer was moving so slow. When I was moving all over the place, it's only when I watched the second screen that I realized when I pointed it that the pointer wasn't there.
So I didn't really catch about the 1.4. If you just explain.
Okay. If here's, you're seeing this pointer right now, right?
Yeah.
Right. Here is 20 volts. Right? For TR2 to conduct, what must the base voltage of TR2 be?
0.7.
0.7 more than the emitter.
Yeah.
Right? So the VBE here is 0.7. So if the emitter of TR2 is at 20, here is now at 20.7. If here is 20.7, for TR1 to conduct, here the base of TR1 has to be another 0.7 higher than that, which is 1.4 in all. So 0.7 from here to make this one conduct, 0.7 from here to make this TR2 conduct.
No understand.
Right? So that is why the output here has to be 1.4 higher. And the op amp will maintain that because of, as I say, trying to, we have a sensing input here that is between the two 5K resistors. And then you have here that is fixed by the Zener. So in other words, if the Zener is, what's the value of the Zener in the question? I didn't check the Zener. Did it tell you the question? Did the question say what value Zener it was?
Yes, no. I think we had to calculate that.
Right.
which is half of the VO, which is
Right. Okay.
10
So
volts.
okay. So let's say you pick a 10 volt Zener, therefore. So it means that the voltage at the input here is 10 volts. Because you use two 5K resistors here and here, once the output is 20, it means this point here is also at 10 volts, right? So if that is the case, then the amplifier, the power supply is working. Let's say something happens to make the output voltage increase. If that happens, then the voltage at this point here will try to go up. This is supposed to be half the output voltage. So if the voltage goes up from, instead of 20, let's say it goes up to 21. So that point in time, this point here is going to attempt to go to about 10.5 volts. But the op-amp needs to maintain that at 10 volts because of the virtual load behavior. So as soon as that starts to happen, the op-amp is going to drop the output voltage now to bring here back down to 10. That's how the regulation works, right? Or if the voltage went down, it means that the voltage at the point at between the two 5K resistors, let's say the voltage went down to 18 or try to go down to 18. It means that the voltage at that point is going to be 9 volts. The voltage at the Zener is going to be 10. The op-amp needs to have those two voltages equal. So it's going to increase the output because of the op-amp behavior. It's going to increase the current drive and increase the output voltage to get that point back up to 10 volts. Meaning that the output will go back up to 20. Yeah? So that's how the op-amp behavior works. That's the function of the fundamental thing with an op-amp. Once an op-amp is working, it does all of its behavior is to try to make these two voltages equal. The differential voltage here, it tries to make it equal, right? And if it is not equal, then the output adjusts in such a way through whatever feedback resistors it has to try to make those two voltages equal again. We have, in the power supply, we fix one of those voltages with a Zener. So the other one is free to vary. But as it varies, the op-amp attempts to keep it back down. So by forcing here to be 10 volts, this is a voltage divider. So if the op-amp forces here to be 10 volts all the time, here must be 20. Right? If you had used another value, then diode, let's say you had used a 9-volt diode, then the op-amp will try to make here 9 volts. And if we need 20 on the output, then we're going to have to change the resistors. Instead of 5K and 5K, we're going to have like a 5K and a slightly bigger one. Okay? But the same principle, if whatever the value of the Zener diode voltage is, the op-amp will try to maintain that at this point here. All right?
So, question, right? I kind of forget this, but how does the Zener diode maintain the voltage at the non-inverting input of the op-amp?
Right. The Zener diode, notice what is, if you take out the op-amp, notice what we have. We have the Zener diode connected to the output, the power supply here. Mm-hmm. What a Zener diode does is, once a Zener diode is provided with the current that it needs to turn on, you know, it's a reverse bias diode, right? Once you supply the current to the Zener diode to turn on, the Zener diode, the breakdown voltage of the Zener diode is once it's turned on, that breakdown voltage appears across the Zener diode now all the time. So in other words, this point here, once I turn on the diode and provide enough current for it, which is through this resistor here. Once I provide enough current to the diode and it turns on, then the characteristic of our Zener diode is that the voltage at the cathode is going to remain at some voltage relative to the anode all the time. If it's a 10-volt diode, it means that it's going to maintain a very accurate 10-volt drop across the Zener. We've grounded one terminal here. So this other point is going to maintain itself at 10 volts. Right?
Yeah, yes, sir. I understand now. And the resistor just to protect the Zener diode in terms of the current going to
resistor
it,
is to
right?
provide the current required for the Zener to operate normally without damaging it. Yeah, exactly. Right?
And
All
then that
electronic devices have a maximum current and a sort of current range to operate within.
and the current range will be given if we get a power supply question.
Yes.
Okay.
Right? But typically for most of these, if you check the notes and so on, most of these diodes and so on need like about 10, between 5 and about 20 milliamps to operate. So you're safe to assume, like in this question here, this one was an assumption that you assume 5 milliamps for it, right? Typically between 5 and 20 is what most Zeners do. I will usually tell you that, but simply because if I have a class of 100 people and everybody picking a different value, it means that all the values, all your answers are going to be different. So I will usually tell the class that that the Zener diode is assumed that it needs 10 milliamps or 15 or whatever it is to operate, just to make marking easier.
Okay, understood. And one more thing, right? By adding the op amp, what protection does that provide? If you don't mind me asking.
It is providing absolutely no protection at this point in
No
time.
protection, okay.
What it is trying to do is to regulate. So it's keeping that V out constant. Under you have designed a 2-amp power supply, so it's going to try to keep the V out, the 20 volts constant. It's doing nothing about the current, right? The op amp is just regulating the voltage. The protection now has to do with current. If we are asking the transistor TR2 to conduct 2 amps. If we short circuit that power supply on the output, the op amp doesn't care. The op amp is internally limited to provide maybe 100 milliamps maximum here. Right, so that's not going to worry the op amp. You could do what you want here. But short circuiting here is going to ask TR2 to provide current into a short circuit. And if you have no protection, either a fuse or over current protection, then the transistor will burn. Right, so the op amp is regulating the voltage, not the current, and it's providing no protection. Remember, the protection circuitry is always over current protection. Yeah.
Yes, sir. Thanks.
Sir, I just have a quick question. So, question B, why is V out equals to 1? For
part B here?
Yeah.
Why is V out?
Further down, in between R3 and R1.
Just now, hold on. Let me just check that. Half a second. Yeah, let me see what we have here. So V out is, oh no. V out is equal to, remember what I just said, that once you establish the Zener voltage, then you set this point at the Zener diode voltage so that V out is equal to VZ by 1 plus R1 over R2. So what this is saying is that the relationship between R1 and R2 is 1. Not that V out is 1. That's what the sign is saying. So from this, we get that the relationship between R1 and R2 is 1. So in other words, R1 is equal to R2. If we had picked another value instead of Z, instead of 10 volts, if I'd use a 9 volt Zener instead, then the relationship between R1 and R2 would not have been one. It would have been something different. So you pick one, you pick a value for one, and you calculate the value for the other. Right? This is not saying that V out is one. Fair enough?
Okay, I'm not following.
Huh?
I'm not following. Could you
Okay, let me see if I can pull up that somewhere. Right, let me see if I can do something. Right, so we have, let me see if this will work here. So we have the output here. We have that's not sure. Draw not a little bit. Eraser. Okay, it don't matter. Right. So this is VZ here. And here we have two resistors, R1 and R2. And this is V out here. And this is ground, right? Fair enough? What we want is that because of the amplifier, I kind of have it inverted here. But one input of the amplifier is at VZ. Because of the virtual earth behavior, if you watch the diagram, this point is also VZ, right? Yeah?
Yes, sir.
Right. So if here is VZ, then the current through R2 is VZ over R2. So therefore the voltage V out is this current, because this current is now passing through both R1 and R2, is this multiplied by R1 plus R2, right? So V out is equal to that, which is equal to VZ into 1 plus R1 over R2, right? Fair enough? So V out is equal to VZ into 1 plus R1 over R2. If I pick VZ as 10 volts and V out as 20, it means that 1 plus R1 over R2 will be equal to V out, which is 20, over VZ, which is 10. That is equal to 2. In other words, R1 over R2 is equal to 1, or R1 equal R2. Yeah?
Yeah, I understand now.
Right. If I had chosen a different value of VZ, let's say I had used a 9 volt Zener, then what would happen is that 1 plus R1 over R2 would have been 20 over 9, which is whatever that is, 2 point whatever, 2 point something. So that R1 would have been 1 point something R2. So whatever you pick, you would have chosen a value for R1, let's say 5K, and now R2 would be 1 point something times that. That's all I say. Right? The question, they think didn't say that V out is 1. You understand?
Yes, sir. Thank you.
All right. Okay, any more questions? Let me see if we'll go back to the.
So it have a past paper question from 2013 just now. Yeah, the 2013 paper question 1 is about a wind bridge question, but I think it have an error in the solution. If you could pull up the solution.
The 2013
solution, yeah. Past paper solution.
Okay, hold on, let me. Close the whiteboard here. You said it 2013
solution.
Okay, just now I don't have that. I'll have to check back that. No problem. I think you had put that on the in the chat.
Yeah.
Or I mean on the spreadsheet. I'll check it. I actually don't have the 2013 solution with me on this machine. I'll have to download it and get back to you. But what exactly? What was the when you said there's a problem? Maybe right.
For the Z2, right? It's supposed to be 2R times 1 over 2SC all over 2R plus 1 over 2SC, right?
Mm-hmm.
He have in a solution 2R times 1 over 2SC multiply by 2R plus 1 over 2SC when it's supposed to divide it. And that kind of, by doing that, it will show off the result solution.
Okay, I will find, I thought I had it printed too here to see, but I don't. I will let me find a solution and I'll see exactly what you're talking about, and I'll respond either to you directly or if you're correct, I'll tell everybody in the class as well. Okay?
All right.
All right. Okay, so great. We went past 11. That was not bad. So again, well, this kind of thing, we'll meet again on Friday. If you have any, as you go through, if there's anything that you need some clarification on, I will put together some sort of revision type questions to help people along the way over the next week or so as you continue the revision. All right. But again, if you have any issues in between, feel free to send me an email and a snapshot of what you're talking about, and I could I'll try to clarify it for you. All right.
All right.
Fair enough.